The success of Apollo was preceded by precursors. When we were trying to land on the moon with men, we didn't even know if we could do it without the vehicle sinking into the surface of the planet. But it was through robotic precursors that we were able to gain the engineering boundary conditions, those early information in order to enable human spaceflight. More recently, with Constellation, we've identified that same need, sending precursors to the moon in the form of LRO and LCROSS. Again, two very successful missions that are providing tremendous data sets, providing that engineering knowledge that would be necessary to send human beings back to the surface of the moon. In this new era of exploration, we now have more diverse targets, more diverse destinations. We have NEOs. We have, once again, we still have the surface of the moon as a candidate. We have the vicinity of Mars, the surface of Mars, the moons of Mars. And so, once again, precursors are here to enable human exploration. So by way of introduction, NASA is planning to have a steady stream of these precursor missions in order to handle these various diverse candidate destinations for human exploration. We call this effort the Exploration Precursor Robotic Missions. Now that's important because a little bit of taxonomy gets a little confusing. This actually consists of two proposed programs, xPRP, which will consist of larger flight missions, instrument developments, and a good RNA R&D effort in order to support human spaceflight. And xScouts, a very focused, small, highly competitive, very aggressive set of missions in the range of $200 million or less, in order to really try to springboard off some real innovation, in order to do some more threshold measurements, springboarding off of the successes such as we had with LCROSS, and really opening up the possibility for the community to be really participative in that. Now these two programs have notionally been assigned to two centers. The XPREP, which is the Exploration Precursor Robotics Program, is currently slated to go to Marshall. And we've set up a center planning office there, and leading that effort is Paul Gilbert, if you could stand up. So once again, as Chris and others had said, if you have any tough questions, Paul's your man. And the xScout program would be set up at the Ames Research Center, and the center planning office for that is being headed up by Pete Klupar. And again, if you have any difficult questions on xScouts, please see Pete. So these two programs together consist of an overall campaign of precursor missions. What I'm going to show you today is basically what the overall scope of this would entail, a proposed point of departure timeline for these two programs, and talk about a little bit about the requirements. And I also like to talk a little bit about what we anticipate getting underway in terms of planning activities in FY10. So why precursors? Why xPRM? Now, I don't mean to jump ahead of what the Human Exploration Framework team is doing. They're developing the overall framework for human exploration. They're developing the overarching requirements, and that's an ongoing process. Again, we are at a point of departure. This is a snapshot in time. However, we think that these general top-level human exploration needs of safety, sustainability, capability, and planning are probably going to exist in the final set in one form or another. And if we take a look at those top-level human exploration needs, and we take a look at where precursors fits in, what we're doing with these precursor missions is we're identifying the hazards that can pose threats to the safety of our astronauts. We're identifying resource characterization that can enable us to be producing fuels on distant destinations that will lead to sustainability of a campaign. We're also doing the engineering boundary condition identification. Again, if you know what you're doing, or if you know what the design criterion are, you can back up and reduce margins, make more intelligent designs, have better, more sustainable architectures because you have that additional information, which leads to sustainability. And of course, all that information leads into the development of capability. We feed back into the technology development area so we know where to focus the efforts. And of course, Because we're flying, we've got the opportunity for technology infusion and demo. And we've talked about demo quite often, but we would like to really be aggressive in terms of infusing this technology so that there's not that valley of death for technology that can't get promoted into actual operation. We're looking forward to incorporating that into the actual critical path or just off critical path of our missions. And then the last opportunity, of course, all of this feeds into planning, but very specifically, the robotic precursors provide the opportunity for us to get the reconnaissance data in order to try to select targets, whether they be multiple asteroids, whether there are different locations on Mars or different locations on the Moon. We can use this information in order to make our planning decisions. So, don't we already have a robotics program? I get that question a lot. Science Mission Directorate has had a tremendous level of success with the various programs, amazing robotic investigations there. But the point is that xPRM is focused on human spaceflight needs, goals, and objectives. Science is primarily focused on scientific objectives. It makes sense. Whereas the scientific community is looking at the National Academy's decadal surveys to guide what they're doing, what we're looking for is what is it going to take for human beings to do what they need to do. Now, obviously, there's a level of synergy that can occur. We see that with LRO, for example, a wonderfully dual-purpose spacecraft that the instrument suite is very compatible between the objectives of both human spaceflight and Science Mission Directorate. And in that particular case, it's an ESMD mission right now, and before this year is out, it'll become an SMD mission. There is the opportunity for collateral benefit. And where there is collateral benefit, we will make we'll make intelligent decisions in order to leverage that capability. But be very clear that the objectives are different, and that's why there's a separate robotics program, or a potential robotics program for exploration. And we can even look at one particular sample topic. If you take a look at the oxygen content in the regolith on the Moon, well, clearly, from a scientific standpoint, it's very interesting. It talks all about the potential sources and sinks of volatiles on the lunar surface. Very interesting stuff. From an exploration standpoint, though, we need to know, okay, how much is there? Can we get to it? Can we mine it? Can we use it? How do we use it? How is that going to make our architecture sustainable? Those are the differences in the questions that we're asking. So the top level objectives and principles. Number one, precursor investigations. We're looking at the precursor measurements and experiments to support human exploration. And what do I mean by that? You already saw a little bit earlier with the charts, but just to go over it one more time, the engineering boundary conditions. I'd like to quote actually a member of the audience, Dr. David Aiken, Aiken's Laws of Spacecraft Design. I'm sure that many of you have seen that out on the web, or maybe have a copy posted to your bulletin board, as I have for the last 20 years of my career. But engineering is done with numbers. Analyses without numbers is at best only an opinion. And so that's what the precursor investigations are doing. They're quantifying those engineering boundary conditions in order to allow us to do the engineering which is necessary to send human beings to these remote destinations. Identifying hazards. We're talking about dust. We're talking about toxicity. We're talking about the hazards of being able to land 10 to 50 metric tons on the surface of Mars, which is significantly different than landing 1 metric ton on the surface of Mars. To identify the resources in order to sustain an architecture, in order to lower launch masses by potentially developing fuels in remote places so that we have the ability to get home without having to take the fuel with us to do it, and to live off the land. And of course, once again, to provide that knowledge in order to inform that selection. The Moon's a big place. There's a lot of very interesting places to go. Mars is a big place. There's a lot of interesting places to go. There's a lot of very interesting NEOs out there to potentially send human beings to. Where do we want to go? We need these precursor missions in order to answer those questions. And a very, very close second is that flight technology demonstrations, to bring that, the technology development, get it into flight and into operation. Now, in the course of these objectives, we have some very strong principles to coordinate with our other NASA directorates. We clearly have multiple flight activities going on. We have to coordinate. We want to make good use of the taxpayers' money and get the best return on our investment that we possibly can. Fostering competition, and this is across the board. This is commercial, this is academic, this is all participants. We want to foster competition in terms of the missions, primarily with the exploration scouts, the payloads applicable to both missions, the investigations. We have a lot of innovation out there, and we want to make sure that we make good use of it. To foster opportunities in international collaboration, we as a country have identified that we need to extend a hand to our international partners, that we need to take a role in engaging our international partners as we go out to explore space beyond low Earth orbit. And of course, to foster participatory exploration activities. We've got workforce issues. We've got to make sure that we've got the engineers out there in school right now to replace us. And engaging them in a real way is part of the way to do that. So, draft level 0 requirements. Again, I don't want to get ahead of what the HEFT is doing. Okay, but if we do take a look at those human spaceflight objectives, they're defining those. And what we have to do is not accomplish, in xPRM, we would not have to accomplish those human spaceflight objectives per se. What we have to do is take a step back and say, what do we as robotic precursor missions need to do in order to enable the human beings to do their job? And so by going through a series of literature searches to identify the existing and notional needs, goals, and objectives for human exploration to Mars and to the Moon, taking the needs, goals, and objectives that were derived for Constellation, culling that down, and then trying to take a step back and identify what the precursor robotic missions would need to do, is how we arrive at these level 0 requirements. I'm not going to go through all of them, but there are a couple that I do want to point out. Number one is that diversity of missions, right up off the bat. Near-Earth objects, Mars, moons of Mars, and the Moon. Future human exploration, potential destinations. This is very exciting stuff. And of course, I already talked about the two programs, but the third comment that I hadn't made yet, we want good launch tempo. Between those two programs, we've got a requirement, a notional requirement to launch at least, on average, once every 18 months with a goal of at least once a year. This will be a continuous stream of precursor information coming in order to fill a pipeline, a pipeline that can service the engineering activities, the planning activities, engage people on a regular basis. And there's lots of opportunities along that cadence for us to collaborate, to partner, to compete. So, to introduce the programs. Again, xPRM is the overall umbrella consisting of two programs. xPrep is the larger of the two programs, and this consists of three primary parts. The flight missions, which I'm going to talk a lot more about later, so I'm not going to talk a whole lot about that right now. Instrument development. This is a wonderful opportunity for partnership. What we're talking about here is funding a line explicitly for the purpose of the development of human spaceflight instruments to be flown on missions other than our own. This is to open up opportunities for us to put an instrument on an international opportunity, to put an instrument on a commercial venture, to put an instrument on a science mission directorate mission. And similarly, in the overarching strategy on our flight missions, we would allow payload allocations in order to try to collaborate in a reciprocating fashion to receive instruments that on our payload opportunities. And then, of course, a very solid research and analysis for exploration. This is taking the raw data and turning it into the strategic knowledge for exploration. This is turning ones and zeros in the PDS into real engineering numbers so that we can really get our work done. And then the exploration scouts, which I had also indicated again, and I'll talk about them a little bit more, but again, very highly competitive, higher risk missions, threshold investigations, very exciting stuff. So, the flight missions and instruments, again, just in the hierarchical structure, we're seeing this again, and I'll talk about it later, but those flight instruments, missions of opportunity for ideal partnerships. And so I wanted to define that term MOOs, because you're going to be seeing it a few times through here. That's missions of opportunity. And once again, very competitive. We want to compete almost every one of these. And we probably do it in some type of salmon-like call that SMD has used very successfully in the past. The research and analysis will consist of a larger set of components. We have the exploration mapping and modeling project, notionally. This will be derived from what we currently have under the old Lunar Precursor Robotics program, the LMMP, or as Mark Robinson likes to refer to it, LMMMMP. A few too many M's in there. But what we're doing with this is we're taking the data out of the PDS. And if you've gone out to the PDS, you know it's a wonderful wealth of data, and I frankly can't make heads or tails of it. But this will allow the people that are doing the work, who are not scientists, who do not know how to navigate the PDS, and bring this data available not only to those engineers, but also to the public. They've got a lunar mapping and modeling portal, which is going to allow the public to go out and take a look at what are all the features of the moon, and we want to expand that in order to be looking at the features of Mars in a very interactive way, to take a look at the NEO imagery and the data in a very interactive way. And so the XMMP would be providing that. Data systems. We anticipate generating a lot of data. And we're doing it right now with LRO. The LROC images are fantastic, and there's so much data we had to add a node to the PDS server. So that's what that element of the RNA is about. We're anticipating having to take care of the data that we're getting down. Institutes and workshops. The NLSI has done a wonderful job of setting up destination-oriented workshops that functioning as an institute in order to, again, to perform the research and analyses, the non-flight hardware in order to provide added value to the lunar data sets. We'd like to expand that. Now, we perhaps would recast an LSI, add nodes, add a NEO node, add a Mars node. That's one option. We could try to do another institute separate from an LSI. The trade space is still open. There's obviously pros and cons of doing each. The next is sensor technology development. And this one's unique. This is not the instrument development I was talking about before. But this is the early technology development in order to try to develop the exploration-specific sensors and instrument developments. High-resolution optics. Miniaturization of wet chemistry labs, things of that nature. That would go under that line. And then, of course, research investigation, grants. Okay, we're very familiar with the ROSES process that SMD has and the laser grants and things of that nature. This is providing that foundational knowledge needed to interpret the mission results and then translate that into real strategic knowledge for exploration. Now, the X-Scout program, again. So here we have the option. A lot of these are going to be PI-led, which is different than we've usually done business. We still might, the trade space is still open. We might want to try to direct a couple of these to some internal NASA centers, but the main focus of these things is to get that innovation, to get that competition, to get a vehicle to do a meaningful investigation outside of LEO for under $200 million, and we think that people can do it for a lot less than that. In terms of planning, what we've assumed is, okay, at a $200 million rate, assuming about $50 million for access to space, and there's a variety of options that can allow that to happen, that we're figuring on a cadence of at least one every 2 years. We'd like to do a lot better than that. In this area in particular, with this level of innovation, we really, really want to hear your ideas in the one-on-ones tomorrow. We want to know what's attainable in these very low dollar amounts. And again, just because they're small, just because they're high risk, doesn't mean that they're not important. They're vitally important. What we're talking about are measuring those threshold measurements, those yes or no answers, is where the X-Scouts are really going to excel. When you're developing an architecture, and you could go one way or you could go another way, if we just knew whether or not the concentration of water was X. Very specific, threshold measurement. You get a Scout mission in there, you get that answer, and you've informed an entire architecture for under $200 million, and hopefully a lot less than that. And of course, the X-Scouts, because of their higher rate of cadence, can be used to complement the portfolio of xPRM, or of xPrep. Sorry, I got caught in my own nomenclature. So whereas xPrep, who can't afford to get as many missions off as quickly as the Scout missions, may be focusing on NEOs, xScout could be focusing on the Moon. They can be complementary portfolios, and we would try to write the AOs for these missions such that they complement one another and address the key questions that the architecture development would be looking toward. Oops. There we go. So, point of departure. This is about the fourth one. This is going to change again. Okay, I can almost guarantee that. But we wanted to give you a snapshot. We wanted to show you what we're thinking, to give you an idea of what kind of scope, what kind of diversity that we're looking for, what kind of investigations are we looking for. And now we're opening up in this workshop the opportunity for you to tell us what wonderful investigation should be going in here in place of what we have here. Or, if these are the right ones, we'd like to hear that too. Okay, we're still working on whether or not the budget will actually close on these. It had for a while, and as we keep looking into it, then we realize, well, maybe we kind of were a little too optimistic there, and so we've shuffled things around a bit. And again, this is a snapshot in time. This is not in stone. So, the first mission, very exciting, return to a NEO. Some type of exploration rendezvous orbiter, notionally. Something Discovery class, something similar to what NEAR did, but once again, focused on the human spaceflight objectives. And so what are those objectives? Well, we're there to identify what the hazards are going to be. When you fly up to a NEO, are you encountering a particulate cloud, something that you're going to have to be shielding against? Are you going to be able to, are there other orbiting bodies there? When you touch it, is it going to come apart like a dandelion field in a spring breeze with these loosely bound objects? We have to understand proximity operations. These gravity wells are not easy. Quantifying those engineering boundary conditions, and then also potentially looking for resources. Now, do we know that human beings are going to be doing ISRU on asteroids? Well, no, we don't know that yet. We've got another separate process that's going to identify that. But while we're there, we know that hazards are going to be important. The ability to do proximity operations is going to be important. The ability to understand those engineering boundary conditions is going to be important. So what kind of measurements are we looking at? Obviously, imagery. Sub-meter per pixel imaging, multiple colors, topography, compositional mapping for any number of approaches, sounding imaging, SARs are among the possibilities. A NEO mission in 2014 yielding results in the 2015-2016 timeframe is perfectly timed to send a human being to a NEO in the 2025 timeframe, allowing us to do a precursor mission here, perhaps another one in the 2019 timeframe in order to refine what measurements we're taking as we understand the scope of our requirements better. We also have other options too. I mean, I've indicated this notional discovery class, but there's nothing that would preclude us from designing something with a slightly smaller payload scope, but increasing the diversity. Something like a stacked set of spacecraft to go to two separate targets. Perhaps be even more aggressive. Do something on the order of 3 to 4 spacecraft, investigating multiple targets. And again, this is a snapshot in time. It's a snapshot in time. We have to determine the viability of how this works and how it fits into the budget wedge. Teleoperated lunar lander. You know, we say, well, why do you want to go to the moon? We're already there. Well, yeah, we're there. Now's a really good time to get the ground truth on what we've got in orbit. LRO is producing a tremendous amount of data to actually land and get the ground truth, to verify that, to confirm those data sets. It's a wonderful opportunity. People are excited about the moon. LCROSS made the discovery of 15 gallons of water within the field of view during that impact. MCube made the discovery of water in areas that aren't even in permanently shadowed regions. The press has been alive with, it's a new moon. So now's the time to strike on this, to get that ground truth on that. And not just that, but to do it in a really exciting way. To take the MSL mass cam camera, put it down on the lunar lander. 3D high def. Now that's a great participatory exploration opportunity right there. Avatar quality graphics. It's really engaging. Once again, we want to be measuring the hydrogen content. We're getting a lot of good data out of LEND on LRO. Let's get down there with a dynamic albedo spectrometer and actually try to get some more indication, some ground truth as to that hydrogen that we didn't know would be there in those sunlit areas. Volatile, excuse me, volatile mass spectroscopy. In situ radiation experiment. LRO is discovering some really interesting things about the radiation environment coming off the surface of the moon. Unexpected stuff. It'd be really nice to get an instrument down there in order to verify. In situ resource utilization. You heard Chris Moore talk about the wonderful developments that have been going on in the ETDP program. We need to get those folks up there. We need to get them up there and doing the experiments on the moon in order to start demonstrating some of these in flight. I mean, Hawaii is nice, but the moon is a little cooler. Sampling arm is a possibility with a microscopic imager on it. And of course, an allotment, again, for partnering payloads. We want to make sure that we provide the opportunity for Science Mission Directorate, for internationals, to all be working together on this, and so we want to go down together. Surface mobility experiment. We've got a constrained budget, so we're looking, we're thinking probably a Sojourner class rover. Very little payload capability, maybe one or two instruments. Very specific we're going to have to get here. Maybe a dust particle size analyzer, an alpha particle X-ray spectrometer, something that fits within that 1 or 2 kilogram kind of payload for that small rover. And of course, we put a context camera on it so they could look back and forth. And I know that I've got one of those tiny little high-def cameras, so there's no reason on Earth that one probably couldn't be a high-def as well. 3 channels of high-def coming down from the moon. Pretty exciting stuff. So how do we do that? Well, another opportunity for interdirectorate collaboration and technology infusion. Optical comm. Put it on the lander. Now, it does limit our landing sites quite a bit, and we still, once again, we're looking at whether or not this architecture will close, but it's another opportunity to start infusing some of these great technologies that we know that we're going to be needing and providing some really exciting output as a result. Mars Orbiter 2016. And we took a look, obviously, at trying to do something at Mars earlier than this, and it's just, really too late for us to try to be looking at opportunities earlier than this. And quite frankly, a 2016 opportunity, we're kind of late, even now. I know that the Science Mission Directorate is already selecting instruments for their 2016 mission. So we've got it in the trade space right now. Again, this is all subject to change. We have to take a look at how things will fit underneath the budget profile. But we've got a couple of options here. First option, this is the one that would be more favorable, some type of resource explorer. And you say, well, why are we doing another Mars orbiter? Don't we have MRO up there? The Science Mission Director has been going there a whole bunch of times. They're not looking for resources. They're not looking for the things that we're looking for. They're not looking for the hazards that can affect a 10 to 50 metric ton landing. They're looking for the things that could affect a 1 metric ton landing. And then they're designing so that they can handle it. Well, it's a lot tougher to land 10 to 50 metric tons. And so we need to do additional type measurements. We need to take a closer look at resources. And so we've got a candidate list of instruments there that you can read as easily as I can read them to you. And of course, we have another opportunity for optical telecommunications demo. But again, this one's a really tight fit. This one's a really tight fit in this portfolio. And so if you've got ideas as to the ways to meet these objectives really, really inexpensively, we really want to hear it. Another option, sample return. Very exciting. Never actually land, just skim through that atmosphere, pick up dust, bring it on back. We haven't talked about that as much in the study team. We wanted to keep it on the table as an option, but we've mostly been focusing on the possibility of an orbiter. 2018, best opportunity to land mass on the surface of Mars in 30 years. 3 times the landing capability that we have in 2016. We think that this is kind of important. And we really want to try to prioritize a way to make use of that. Now, since it's further out in the timeline and there's larger budget uncertainties and we're still working on the front end of it, we really don't have any clear ideas as to what we want to do with that yet. But An initial first cut would be like a Mir-class rover, and again, it's because we're looking at missions that are on the order of $800 million or less. And going to Mars is expensive. We want to hear how you would make it less expensive. And again, we'd be focusing primarily on resource-type investigations and hazard investigations primarily, focusing on the NRC Safe on Mars objectives, for example. And of course, we'll be assessing the EDL. Oh, EDL. I missed a point on the last chart. Another opportunity to infuse aero capture with this orbiter. Not a demo, fly-along demo. We actually looked at the fly-along demo, and the fly-along demo turns into its own spacecraft and becomes really, really expensive because you need all the subsystems of a spacecraft on the experiment. It's actually less expensive to go for it, to infuse it. And we're still looking at exactly what the risk posture with that would be, but here's an opportunity, again, to infuse that technology, to take an incremental step forward in order to enable the objectives of FTD even better. And then, again, to enable the human spaceflight activities even better. So then 2019, now we're really getting out there. So what exactly would we be doing with that? Again, a NEO mission, something that would springboard off of what we were doing in 2014 to better inform a human exploration in 2015. And in fact, maybe we kind of got this order reversed. We should probably be doing, a diverse setup at the front, and then a more toned or more specific set, more of a discovery class on the later part. Again, we're looking for your opportunities. What kind of investigations would we be looking at? Again, proximity, remote sensing, possible beacon emplacement, small hoppers, touch and go, grappling. How do you anchor to one of these things? Do you want to anchor to one of these things? Sample return. Resource relevant sample return. Now, once again, this is a dual use thing. You say Science Mission Directorate, they've got missions, potential missions that might be going off to NEOs. Is there duplicity? Yeah, to a degree there might be, but the objectives are different. The objectives are different, the investigations are different, and that's why we're doing it, because we want to send human beings there. So what are we doing in FY10? We've got a lot of work ahead of us, and the programs don't exist. These are proposed programs. But if we're going to meet the aggressive schedules that we've been trying to lay out for activities in FY11, we have to do some precursor work to our precursor missions. And what that includes are mission definitions. We need to take the input that we've gotten so far from the study team. We need to take your input from this workshop, from the RFI. We just released an RFI on Friday. It's a little bit late in the game for this workshop, but it's out there now. And so we're looking forward to getting your inputs on that. And then folding that in and developing what we're referring to as objective definition teams. In the Science Mission Directorate vernacular, that would be the same as the science definition team. We're going to follow a very similar model, and we did it for LRO. And even though we have a very, very aggressive schedule, so did LRO. And we constrained it, and we were actually able to get a good objectives definition out in a fairly quick fashion. We're anticipating trying to do that again here. And we also need to do some mission concept studies. We've got to put some numbers behind this engineering. Engineering without numbers is opinion. And so we're going to be working toward that. Then, once we have those top-level objectives that we need to do with proof of existence concepts, notional payloads that we know can make these observations, then we have to have a functional acquisition strategy meeting. This is where we're going to be deciding where we're going to be doing things. Are we going to make it? Are we going to buy it? If we're going to buy it, is it going to be a AO? Is it going to be an RFP? Is it going to be a sole source? Because we need to get the ball rolling, and we need this instrument so that it correlates to another measurement. These are the decisions, that we'll be making in the make-buy decisions. Following that, we're going to start doing the AO preparation. When I say AO, that's my generic term for all the procurement documents, whether they be AOs or RFPs or JOFOCs. So that, when we get appropriations, then we'll be ready. We'll be ready, we'll be poised in order to engage in these really, really exciting missions. So in summary, we're poised, we will be, in order to provide this critical knowledge for exploration from a very diverse set of destinations. This is a really, really exciting time to be working here. Again, it's analogous to pre-Apollo. The precursors enabled the human exploration. The proposed scope, again, focusing on human spaceflight objectives while leveraging the unique capabilities of partners and partnerships. And no other program exists fulfills these objectives right now. And is fully consistent with the current best estimate that we have of what human spaceflight needs. Again, precursor investigations focusing on those engineering boundary conditions, hazards, resources, and determination of targets. And a very close second, providing an opportunity for technology demonstrations and infusions. And so here we have a timeline. It's a pretty aggressive one. 2014, a NEO rendezvous. 2015, a lunar lander. 2016, a Mars orbiter. 2018, a Mars lander. 2019, a NEO rendezvous. And throughout that entire thing, we've got this constant line of missions of opportunity. These instrument developments that are going to fly in every mission other than our own. Opportunities for partnership. Opportunities to extend the human exploration, precursing investigations beyond our own program. And then, of course, the X-Scouts. And once again, notionally, we've got that 1 every 2 year cadence. We expect to do a lot better than that. But even with that, that's a pretty admirable tempo. So with that, I think I have time for a couple of questions.
This is David Gump with Astrobotic Technology in Carnegie Mellon.
Yes, sir.
The COTS program and the follow-on fixed-price commercial purchases are likely to really bring down the cost of getting people and cargo to orbit. A similar approach for the moon with fixed-price commercial purchases could have more impact on affordability than any one technology that's under development. But your slides don't mention commercial at all. So I'm curious what your plans are to use that tool to bring down costs.
Okay. We took a lot of look at commercial partnerships and exactly what commercial partnerships means and promoting commercial activities. The study team didn't really look at seeding a lunar lander capability in the same way that the COTS program seeds the commercial crew and COTS option. That's not the focus of xPRM. However, in xPRM we do look at the possibility of using such a capability were it to exist. We get a lot of questions with respect to the lunar lander versus the Google X Prize. A lot of folks have asked, why, what's the difference? Well, they're both landers, but a lander's just a vehicle. Well, they both have cameras. Well, everything has cameras. Well, they're both teleoperated. Well, we don't have a lot that's fully autonomous. But that's where the similarities end. The xPRM objectives are to do the precursor investigations. Without the precursor investigations, it's not in my charter to do the mission. I need to be able to get the ground truth on the volatiles. I need to be able to prove that that we have the ISRU capability. If the Google X Prize develops a technology that demonstrates clearly that we can land very, very inexpensively, we definitely want to make use of that. And that's exactly where the X-Scouts would come in. There's nothing at all that would preclude Google X Prize teams from proposing on the Scout missions and having a very good chance of winning for that level of innovation. We also looked at the possibility of commercial data buys. And we've got very limited experience with that, mostly in the Science Mission Directorate. And it's been a varying track record with levels of success with that. So we didn't have enough data to really evaluate it fully, but we definitely are making a recommendation to management that it is something that is definitely worth keeping an eye on as we progress, because there's a significant potential that, you know, it would be wonderful if we were able to just say, look, we need imagery of this site. If there's a commercial capability that is in orbit around the moon, great. You know, we can do commercial data buys. We've done it. And again, the culture is evolving. The capability is evolving, and the desire of commercial to provide those services and for us to be able to step in and just buy them is evolving. And I think that's something that we have to keep looking at. But right now, to answer your question very specifically, the focus of the xPRM right now is to do those precursor investigations. Now, if there's a commercial leveraging opportunity to do those precursor investigations that we may have missed, then I'd be very eager to hear from you as to how we can fold that in order to do the precursor investigation objectives by leveraging from commercial opportunities. That answer your question? No. Any other questions?
Hey, Jay. This is Walt Faulkner in the back. You probably can't see me back here.
Oh.
Anyway, you know, the Augustine Committee in their discussion of the flexible path architecture mentioned two other destinations that you don't seem to have brought up, which include going to Lagrange points as well as going to Phobos Deimos.
Mm-hmm.
So is the intention, was it deliberately omitted from your roadmap or discussion, or are those potential candidates as well?
They're definitely potential candidates. In terms of the point of departure architecture that we had, we don't have anything listed for Lagrange points. And again, if you take a look at what I was talking about, that you take a look at what the human spaceflight objectives are, which could very well be going to Lagrange points and doing assembly of very large items in order to do a low energy trajectory change to another Lagrange point. It's good stuff, okay, and that can be a human spaceflight objective. But if we take a look back, what kind of precursor investigations do I need to do in order to prepare for that? And when the study team took a look at this, we were determining that really what it really comes down to is hazards, radiation hazards. And that's an investigation that we can do on almost any interplanetary mission. By monitoring during the cruise phase out to a NEO, we can probably meet most of those objectives. And then from there, it becomes a pure technology demonstration mission. So I don't want to preclude it, but in terms of the precursor investigations, which is my reason for sending a mission as a precursor investigation, the Lagrange points for the robotics wasn't a strong player. Now, that's not saying anything about the human spaceflight. Phobos and Deimos. Definitely, it can be in the trade space. Right now, with the limited opportunities that we had for the Mars orbits, we were focusing primarily on the resource aspects. We were looking at the objectives that were laid out by MEPEG to identify hydrogen-rich resource areas in 16, and then, of course, getting the ground truth in 18. Because of the fact that we didn't put a Phobos Deimos mission in there does not mean that we wouldn't. It just means that in terms of the priority and the limited budget and on this point of departure timeline, we didn't include one. Any other questions? And 4 seconds to spare.